Ring that bell. Yeah. I remember when that bell showed up. Everyone was so mad. Okay. All right. We were talking about unit tests, right? So here's how we were getting started. Just as a very quick blitz review. Unit test. Okay, this assumes I have my sphere created. Here we need to import unit test. It comes from the standard library, class, and then the convention we have here is name of the class we're testing, test. It's a class, so we follow camel case. And then we see this funny thing which we've never seen before where we've got parentheses next to the class definition. That's where we do like inheritance. Long story short, the magic code. Slightly longer short story is this is a class that if you open up includes a lot of methods. Things like assert equal. But we don't write them, but we want to use them in this class. So we basically, when we do it like this, it's like envision this class exists. We copy all that code in and attach it to our class. We don't see it, but it's there. So we have access to all the methods from this. We are extending that class or inheriting from it. That's what it means. That inheritance is a topic of like 162, so it really doesn't matter, but I'm just letting you know. And then here, we've got a test. Here I'm just testing two little things. Testing the two attributes. The attributes we got are, well, the point 3D, and the other attribute is the radius. And the idea here is, well, like, okay, look, if I make a sphere object, and I want to get its point 3D, I better get the correct point 3D back. If I have a sphere object and I want to set the radius, and I ask for its radius, I better get the right radius back. That's the idea. And we also follow there's a rule and convention here that I'm going to say we're going to follow. Is test underscore, it has to be there. That's the rule. I was saying last time, you can actually change it, but not really on Colab. That would be like a project setting, and we're not tinkering with that. So just say test underscore, that's what you call all your unit tests. Each unit test should test one thing. You don't want to have a unit test like 4 different things and then have it fail and you're left going, what failed? And then you want your names of these unit tests to be hilariously descriptive. Yes, you want all of your functions and methods to have good names, but you'll see here there's a lot going on in these names. But that's important. And the general idea is the what, under what condition, what to expect. Now, in this particular case, there's really no condition to be worrying about. So okay, what are we testing? Sphere's center point returns correct center point. Sphere's radius returns correct radius. And we want these long descriptive names because if one of these tests fails, it's going to say, test sphere radius returns correct radius, failed. I know exactly what's wrong and under what condition. Again, here there's no nuanced condition, but it's helpful to have very descriptive names. Yeah. Okay, and then here's some additional unit tests. I've excluded the previous ones I showed before, but here, test equals on equal spheres returns true. This is perhaps actually not the best name, but we'll stick with it. Returns true, right? Like, okay, two things should be equal if they are in fact equal. So I create two spheres, I assert that they're equal. A, B, that should be true. Test equals on not equal spheres returns false. Do you see now how I'm saying like what condition expected? See what I mean? What am I testing? Equals. On what the condition? Not equal spheres. What do I expect? False, or not equals in this case, right? So assert not equals. Test equals on sphere and string returns false. Okay, great, cool. And then down here, I have like test repr arbitrary sphere returns correct string. Okay, there. So you see the names are descriptive, and I'm also showing you just additional examples of what these unit tests can look like. Any questions about what you're seeing here at this stage? So for those of you that had lab yesterday, you would have worked through doing basically this for that person class you make. For those of you that have lab today, you'll sink your teeth into this and have fun writing some tests. And yeah, like I said, test, method, condition, expected. So test equals, on equal spheres, returns true. The method is equals, or EQ, whatever. The condition is on equal spheres. And what is expected returns true. We could argue that it's like, well, it's not really returning true. We're just asserting that they are in fact equal or not equal. Okay, fair enough, but whatever. Now, sometimes though, like in the sphere class, like we often have functionality we would like to test on various cases. Like we saw the example of the equal, unequal spheres. Okay, fine. But there's going to be other conditions, like diameter, right? What should the test cases be for diameter? Well, maybe we want to check that, like, well, let's check that what happens if it's got like a radius 0? What happens if it has a radius 2, right? Now we could say, do we really need to test when it has a radius 0 versus radius 2 and what the diameters are? Sure, we can make that argument, but the point is maybe I do want to test those two different cases. And maybe what else I want to check? Edge cases and the general case. Okay, test a sphere at the origin that has a 0 radius. Test a sphere at the origin with a non-zero radius. But we may also want to confirm that the center point has no impact on the diameter. So maybe we also want to test on a sphere in an arbitrary location with a radius 0, and also test a sphere in an arbitrary location with a non-zero radius. So do you see how suddenly, like, okay, what am I testing? I'm testing diameter, okay? But there's 4 cases in which I want to test, okay? With these 4 examples, I could do this. There is nothing wrong with doing this. You see, I've got the 4 cases. Test diameter radius 0, origin returns 0. Test diameter radius 1, origin returns 2. Test diameter radius 0, arbitrary center returns 0, and so on. You see, all of those tests test those same things. There's nothing wrong with this. But you might look at this and be like, okay, that's great and all, but is there a better way? Yes, there is. Because, I mean, the whole point of writing these unit tests, like one of the big points of writing these unit tests is like aggregating and collecting the tests together in a nice, easy to understand way. So we might say like, look, these tests are all basically the same test under different conditions, but it's testing the same thing. So can we kind of combine these things? Yes. And we can combine them in a way that, one, seems pretty obvious, but there's a catch that makes it better. The obvious thing is, well, why not just write one test, but have like a for loop that runs the 4 subtests, right? Why not do that? Have one test, like test diameter, and then it has like a loop that runs the 4 subtests. Okay, cool. But with Python just being Python, this falls into creating that little bit of a problem that I talked about of you really want your test to only test one thing at a time, because if it fails, you're left going, what part of it failed? So if I have one test testing 4 different things and it fails, what failed? But there's a quick, silly little simple trick we can do to actually make this not become a problem that's built into unit tests, and I'll show you in a moment. But here's what I'm doing. First, I'm just writing it this way for simplicity. I've got a list of my cases, the spheres. A sphere, origin, radius 0, origin, radius 1, not origin, radius 0, not origin, radius not 0. I had a float there because why not, right? So I just created a list of the different cases. And then I also have a list of expected results for those corresponding cases. Would we agree that this is what I should get for each of those cases, right? Now, if you're saying, okay, but why did you do it in 2 lists? It didn't matter. I could have made these tuples. I could have done this any other way. I just thought it was simple to have 2 lists where like, here's the cases, here's my expected results, and they're like index connected. 0, 0, 1, 1, 2, 2, 3, 3, right? You see my point? But like I was saying, if I were to run this just in a for loop, ignoring this line, if I run this just in a for loop, if this crashes, it won't tell me which subtest crashed. It would just say one of those tests crashed, which is not very helpful. But as long as we write this magical line of code right here with self.subtest, it will work. it'll tell you, it'll run all the tests, and it'll tell you which subtest failed. So it's just the magic trick to be able to use a for loop for having it test multiple cases. Pretty neat stuff, that's all. And if you're sitting here going, how am I going to remember that? I don't know, just after you've done it a bunch, you'll kind of remember it. I'll be honest, when I started talking 2 minutes ago, I couldn't remember what the line of code was that I wrote. I know there was a line of code. So all I would do every time when writing my unit tests, I would be like, what's that line of code? Oh yeah, with subtest. Okay, cool, yeah. That's how you go about doing it. Hopefully by now you're getting a sense of things that you should know and things that like, well, I know enough to go look it up when I need it, right? You kind of have a feel for that at this stage. But let's just explore it, okay? So with, I'm zipping. Remember, who here remember what zip does? Let me remind you what zip does. It's not critically important, but if I have like A equals 0, 1, 2, 3, and B equals W, X, Y, Z, and if I do for thing in zip, A, B, print thing. So this will iterate over the collection of things, but it'll actually like zip them together so we don't get one element from one of these things, we get the pair or the tuple of the pair of things, like so 0W, 1X, 2, and so on. You see? It's pretty handy. And then over here, I could do like thing 1, thing 2, and then suddenly, by doing that like unpacking, don't worry, this is not critically important for you to like memorize or anything, but it's just a handy thing. Basically, I'm looping over the pairs of cases in expected from here, okay? So each one is a case, and what do I expect? Self-assert almost equal expect case dot diameter 5. All right, yeah? Now, you might be saying, what is almost equal? Almost equal, that's what you use when you have floats, right? Because remember, should you use equals equals on floats? It's risky, right? Because that whole funny floating point precision thing. And all of the other like assert equal stuff that we've seen before always had a like expected and what we get. But what on earth is this third argument, that 5? That's the precision. How many decimal points do I care about? Don't worry, this is not something that I would expect you to have memorized. You would look up like, how do I use almost equal? And you would read the documentation. Yes?
What does the width do? Like the width itself dot subtest?
Width. Width is a, doesn't matter. Okay. Don't worry about it. Don't worry. It's the magic code right now. It's a funny Python thing. It doesn't matter. But good question that I'm not going to answer. Yeah. Other questions that I may or may not answer. All right. So the general structure here would be, like here I simplified it without using the zip, is I've got, the way I like to do it at least, is I have my list of cases, my list of what I expect to get. For each thing, with self-subtest, whatever the expected is at index I, the case, and then the floating point precision there. That's the general idea. Without subtest, like I was saying, without subtest, if one of them fails, it'll just say that test failed and you won't know which case it failed on, where this is much more helpful. And then, yeah, here, almost equal is a nice way to manage comparing floats. And we specified a 5. That's like how many decimal places do we care? If they are the same within 5 decimal places, I'm happy. Close enough. And if you're like 5 decimal places, can't we get more precise? That's already past like millimeters, right? Like that's crazy, right? That's we're pretty happy with that. Now, how do you run these unit tests? If you've set up Python on your computer and you have like a nice integrated development environment where you've got your project set up, how you would typically write code, like if you're writing software for anything more than like what we're doing in a class like this, You wouldn't need this magic line of code. You would kind of like set up your project to run unit tests like in a nicer way. But on Colab, this is the magic code. You have your tests written, this line of code. You wouldn't want to put this inside your class. You want it like outside your class, and you run that line of code. And this says, go and run those unit tests. That's how it would work. And we saw an example of that like yesterday or 2 days ago. But here's like, this is what it would look like. If I had my sphere class and I had all of my unit tests and I were to run it, I would see like this. Like, they all passed, great. And if one of them failed, for example, what did I say? If one of the tests failed because I changed the code specifically such that it would fail, it would tell you which one failed. It says failed. Distance between center various spheres returns correct distance. You'll see there's no OK up here, but it's telling you it failed. And unlike with the assert test where it just crashes, this says it failed, and it says because 1.732051, which is what we expected, is not equal to 1.414 blah, blah, blah within 5 decimal places. And it's, in fact, it's got a difference of that much, right? So it gives you a lot more information than the assert test, which is very nice. Cool. Yeah. All right. And it's telling us which subtest failed, which is nice too. Because here, it's saying it actually, because this was one of the ones that had subtests, and so it actually specified which subtest it was that failed, which is kind of nice too, right? It's like, well, subtest, I guess index, case 0, huh? Index 1? That doesn't make any sense. Well, whatever, doesn't matter. Point is, it didn't crash on all of them. It was saying specifically one subtest failed. Any questions or anything? Now, okay, you will need, okay, you will see the output. So writing and running these tests may feel like a lot of work. I'm not going to lie. Obviously, I know you're like, writing these tests is almost as much work as writing the code itself. Yep. And remember what I said. Your code is useless unless you've tested it. And I'm not going to take your word for it. You give me if no one would take your word for it. You provide the unit tests to say, I wrote the code and I wrote the test to demonstrate that my code is correct. Because the tests show that you've spent the time thinking about it. Hopefully the tests are correct, but you spent the time thinking about your tests, your code, about the tests, how they should work under all these conditions, and if they all pass. I'm much more comfortable using your code if you've demonstrated to me that it's also correct than just like, here, trust me. And this is not a me thing. This is not because you're in university. This is how software works. If you're writing code, if you work at a company and you don't write the unit tests, they're going to ask you to leave. So yes, writing tests is a lot of work, but that's part of what you're doing. Don't think that the tests are just like, oh yeah, and the tests. No. That's the other half of what you got to do. Writing code is part of your job when you're a programmer. Demonstrating your code is correct to yourself or anyone else that uses your code is a big part of writing code. Okay? Questions or anything about that? Writing the unit test is one of those things where, like, how do I test this object? What conditions do I care about? Do I need to test this condition and that condition, or only one of these two conditions? Or do I really need to do both? That really is more of an art than a science. That's not something I can give you a concrete answer on in a general case. It's always going to come down to, and it's going to be a skill you develop, and you're only going to develop it by doing it. So it's not like I would say to you on like assignment 4, write the unit test right now and expect you to sit down and start going, no. That's not how this works. That's not how any of that would work, right? In the same way that you don't just sit down and start writing your code. You got to get slow. There's a methodology to it. Everyone kind of works out their own system for writing these things and whatnot. And remember, the point of these tests is also not just to demonstrate it's correct, but it's also to give yourself a chance to be reflective of how your code is operating. Because sometimes just writing the tests, not even running the tests, but the process of writing the tests will be giving you enough information to let you know that you didn't think about everything for your code. Like, you don't even need to know that your code's going to fail the test. You don't even need to run the test. Just the process of thinking about what tests to write helps you write better code in the first place, which is a very important skill to develop. So, develop it. Any questions about those unit tests? Okay, now, we have been working towards data structures. This is basically the subject of all next semester of 162, okay? So we've been working towards this. The class isn't over after this, don't get me wrong, but this has been the big thing we've been working towards. Data structures. You've already seen data structures. Tuples are data structures. Lists are data structures. Sets, dictionaries, they're all data structures. Really, it's just a structure of data. It's a way we are storing data, and how we store the data affects how we access and manipulate and change and whatnot the data. Data structures are a big part of programming. It's like think about it like this, right? We started this semester talking about variables, types, literals. Then we moved on to functions, if statements, loops, right? These are all these tools that we're adding to our tool belt. And all of these things that we learned, I mean, functions perhaps are a little bit different, right? Because you write a function, and then it's like you made a custom tool, right? If you write a function to solve some problem, now you've got this custom tool you put in your toolbox, okay? Now, data structures are like the next big leap of the sophistication of tools. They're classes. We need to know what classes are in order for this to work. But the data structures are these pretty complex tools that we are going to build and add to our toolbox. In general, so let's say you're a software engineer. It's 10 years from now and you're a software engineer. You're going to be using data structures all day, all night. Now, chances are you're not going to go implement your own data structures because all the standard libraries include your general purpose data structures. Because if they didn't, they wouldn't be very good standard libraries because they're such important tools. But you got to know how they work. If you don't, you're not going to have a good time. So at this stage, I could make the argument well, you didn't need to know how a list worked in order to use a list, right? Which is great, and that's true. But imagine being hired to be a mechanic and not knowing how the car worked, right? You're but I don't need to know how the car works because I know how to use a car. But you want to be a mechanic, right? That's kind of what's going on here. It always happens next semester, right? Because it's a class on data structures. Why would I learn how to use a queue? I can just import queue. Well, you're taking a course on how to build queues. And you're saying, why would I build it when I can just import? Then go take another course. Don't take the course on how to build a car and tell me that, well, why don't I just go buy a car? Because this is a course on how to build a car. Because you need to know how to build a car, right? So anyways, data structures. Yes, they exist in your standard library. You got to know how they work, how you build them, because the skills you develop from learning how they work are critical. But I'm going to warn you. They are fairly sophisticated. They are complex. They're not crazy. They're not designed to be complicated, but they are complex. They're not hard, but they're not trivial, okay? So I'm not trying to scare you. The level of detail that we're going to cover in this class, we're going to make a data structure, a fairly general purpose data structure. It's also going to feel kind of cheesy because we're going to be basically hijacking the Python list data structure to make our own data structures, which it's but that's not really making the data structure. You're just using a list to make it. But that's not the point. You're learning how this works. We sink our teeth into all of these concepts a lot more next semester. And once again, raise your hand if you're in 162. Perfect. All right. So yeah, we're going to have a lot more fun next semester. If you're not in 162, you should, because it's way more fun. Okay. All right. Although these data structures had clear functionality associated with them, We use them as like a mechanism for storing and managing data, and they all kind of have their own purpose. Like a list is a very general purpose data structure. But remember how we learned about sets, right? Like a set is great and all, but its use is far more narrow than a list. But when you come upon a situation where a set would work really well, you're going to be really happy to have a set data structure and not have to use a list, right? Like I know those questions were simple, but like tell me the number of unique words in a book. Throw them into a set and count the size of the set. Done, right? Where if you did it with a list, you'd put them in the list, you'd need to keep track of everything you've already seen. It's a whole thing, you know? It'd be a nightmare. Where a set, it's not as general purpose as a list, but its use is exactly what you need it to be when you need it. All right, so yeah, lists are very general purpose. We like them. We have an ability to like arbitrarily index them, assuming that the values exist at that index. It has like efficient lookup. It's easy to search, like a linear search. The data is ordered. That doesn't necessarily mean sorted, but the data has an ordering, right? In the same sense that there is an order to the people sitting in this row right here. Like you're sitting after him, who's sitting after him. You're not sorted in any way, but there is like an ordering, right? If you're in seat 0, the person that comes after you is in seat 1, right? Well, 0 and 1, you know, there's an order. I'm emphasizing the difference between an ordering and sortedness, because there's a difference. All right, cool. So consider a list. They are very easy to index. The lists have a beginning and an end, right? The elements exist in some order, and it's very easy to do a linear search on a list. Great, okay? You've been taking advantage of these features all the way back to assignment 1. Now in assignment 1, you didn't really know what lists were, but not long after that, we learned about lists. Assignment 2, you used lists. Assignment 3, did you use lists? You certainly did. Anyone do assignment 4 yet? Did you use lists? Yeah, you did. Lists, very handy. Data structures, very handy. All right. You've all been taking advantage of these features, but the lists are provided to us at a certain level of abstraction. If you dig deeper, there's a lot of crazy cool functionality happening under the hood of a list that someone had to program. And like I said before, these data structures are an exceptionally important tool to add to any programmer's toolbox. How they work is going to be critical, both in terms of you're going to learn a lot by learning how these things work, in the same way that you're going to learn a lot about how a car works by like building one, for example. But also because knowing how they work also gives you the ability to use them more effectively by just having a better understanding of what's going on. To start learning about data structure, we'll construct our very own data structure. So raise your hand again if you did assignment 4 yet. One person, only one? I'm proud of you. You built a data structure. The country catalog is a data structure, okay? Now you just hijacked a list, but yeah. Here we're going to make a course data structure. It's going to keep track of students in my course, okay? It's going to be a data structure. It's a simple one. It's going to hijack just a list, so it's not going to seem very sophisticated, but it's whatever. It's going to be good. And when I say things like, well, you don't know what's going on under the hood, you've used append, right, for your list. If you append something to a list, how did that work? You could sit there and tell me, well, it just added the thing to the end of the list. Well, that's what it did. How did it do it? Well, I don't know, right? It didn't really matter for our needs. Notice how the what and the how are actually two separate things. You ever notice that? Like, append to a list. What does it do? It adds something to the end of the list. How does it do it? I don't know. Right? The what and the how, and by the way, this isn't a programming thing. This is how you interface with the world around you at an every day. It's helpful to think about it this way if you're like learning programming, because it helps you kind of think about the what and the how and the design of things. But like when you turn the key on your car, what does it do? Well, it turns it on. How does it do it? Oh, I don't know. Right? Like the what and the how are two very different things. That doesn't mean that the how isn't important. It doesn't mean that the what's not important, but they're separate. There's obviously a connection. The what is going to be based on the how, right? But ultimately, you can use a list without knowing the how, right? Because all of you have been using the list without knowing the how. So we're going to start with a super simple class, a student class. It's effectively a data class, a class that just stores a group of data that we want to think of as like a unit of information, right? A student is made up of a couple of pieces of information. It's not going to have any fancy functionality. We're going to have a repr because it's always nice to have a repr. We're going to have an EQ, a constructor. Those things are always really nice to have, but I don't really think we need any additional methodology there, which is also a very common thing. I know, like I was saying, classes are great for combining data and functionality. Turns out we actually kind of hate doing that a lot of the time. We kind of like to keep them functionality and data separate. I mean, it comes down to a design principle. You could talk to some old school programmers that may disagree. But yeah. So it's not uncommon to have very simple classes. In fact, most classes that you would write, ideally, they are hilariously simple. FYI. It's like we don't want these complex things. So let's start with a very simple class. I'm just going to copy it. All right, I'll get rid of the... There. Have a look at this code and ask, take a moment, look at this code and tell me, just look at this code and ask any question you have about this code before we move on. Because it would be important to do that, I think. How many methods does this code have? 3. Let me try that again. I need more, I'm concerned. How many methods exist here? 3. Now, to be fair, you might be like, wait, well, it's only 2 and a constructor's the method. It's a method, right? These are all fancy magic ones, you know, the dunder methods, which I hate that word, but yeah. The initializer is a method. Also, I warned you about this before, but I'm going to warn you again. Did you just take a picture?
No, I'm sending an email on my phone.
Okay, good. I believe you. I just want to make sure you're not taking a picture.
I would not.
Perfect. I trust you. Be very careful not to type int when you meet an int, because underscore underscore int underscore underscore also has a meaning. And you might be like, well, how easy is it to make that mistake? Very easy, because of like tab completion. If you type in like in tab, it might complete to int. And the reason this is going to be a nightmare is because you get an init for free. So if I'm like, okay, I wrote my init, and I'm like, okay, a equals student, no, let's do it like John Smith, J Smith, oops, at email.com. Oh my goodness. And you do this, and you're like, it takes no arguments. And you're like, what are you talking about? Why is it telling me it takes no arguments? It's got, my constructor has 3. If this ever starts happening to you, one of the first things you should go do is be like, did I type int? And I did. Okay. So rerun that. Oops. There. Better. Okay, cool. That was just a warning. Sorry, okay, you had a question. You were going to ask a question about the class before I got excited about asking people about how many methods.
Really quick question. Why is there an escape character in the bottom line of that?
Right here?
Yeah.
Because, so, very good question. Actually, you know what? Let's go through this one at a time. What is the constructor doing? Not much. It takes 3 arguments. It just assigns some values. Be warned, I know so many of the classes that we've written so far, it's a one-to-one parameterless to attribute. That's not necessarily the case. Think of a list, right? A list has a length attribute. When you create a list, do you go and like give it a 0 argument when creating? No, it just knows, right? So sometimes some attributes don't require anything to be passed to it. We'll see an example of that shortly with the course. Anyways, it's a very simple constructor. First name, last name, student number. It assigns these 3 things. Okay, great. Now here for the EQ, If the other thing is not a student, they're not equal. Otherwise, check if their student numbers are the same. You could say, well, why not check their first name, last name, and student number? You're absolutely right. We could do that. 1, I'm lazy. 2, student numbers are really the unique identifier of students, right? So if their student numbers are the same, they're the same. Maybe someone changed their name. But if they have the same student number, it's the same student. Make sense? Yeah. Why are you looking at that? Did you argue with them about it?
No, it's just like last time when we did it out, I did all of them and it makes
Did you? Oh, some of the people, yeah, it's funny. Some people did it that way, and I was like really impressed. And other people, and I was like, yeah, you were writing it out. Yeah. But yeah, there you go. Point being, sometimes, because remember, what does it mean for two student objects to be equal? Whatever I want. I get to invent it. You want it to make sense, and I think this makes perfect sense. It wouldn't be wrong to say if all their attributes are the same, fine, but this is perhaps a little nicer, I'd say, right? Yeah. And then the repr. Before, I was saying when you make a repr, I want like a string representation of my object. And if I don't have an idea in mind for how I want that object to be represented, I follow that basic pattern, which is class name, parenthesis, attribute, blah, 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 close parenthesis, right? But, so you were asking what's with that escape character, right? Specifically, I'm guessing you mean that one? Yeah. Well, that's a tab. Well, I just want to make sure there wasn't another one that I missed. So what's going on here? Well, you'll notice maybe, for whatever reason, I have decided, no, for my program, this is how I want my students represented. I don't want it in that basic format. I want it to be represented with last name, comma, first name, tab, student number. That's what I want. Why? Because I said so. I can make it whatever I want, but that's how I want it. I basically just want it to be like a single record of a student that I could see, right? Like imagine, I can go on like X reports, right? Which is, do you guys go on X reports for things? A student? Okay, whatever. It's like this thing I have access to, and I can see all your little pictures, right? And I get this record of all my students in the class, and it's basically formatted like last name, first name, student number. So like same idea, right? Okay, anyways, there you go. Very simple object. Great. Any questions about it though? Other questions? We had one good one about the tab. It was just because I like it like that. Why 1 tab and not 2? I don't know, we could do 2. Doesn't really matter, we can do whatever we want, right? Why not first name, last name? Sure, fine, whatever. It's whatever we want. So there we go. Here's my student class. There we go. And then the next thing we would do is create the course class. But I think it's worth doing. Let's do another lecture activity. What should we do today? You're scared? No, you shouldn't be. There's plenty of time. It's Friday. It's the wine mixer day.